2. Right, okay. So this is question 2, this guy. Okay, so what you're doing, use part 1 of the fundamental theorem to graph G dashed. Okay. Now, if you are graphing the derivative function G dashed, isn't G dashed just f of t?
Yes.
Okay, so what do you notice about the graph? G dashed is inverse of it, G dashed is the same as f.
Okay.
So that's all that was.
Right. And then for how do I get G double prime? Because
Ooh.
I got G at 3 and then I got G prime at 3 and then the third question is G double prime of 3 and I don't know how to do it.
Ah, okay. I believe that's going to be the answer. Let me check. It's going to be 0. Let's put in a key, put in a solution, see what it does. Lost the downtime. Where is it? Must be down here. Oh, it's -2. I'm wrong. Okay. Why would that be -2? Oh, because the slope of the line at that point is -2.
Oh, okay.
So when you're talking about the derivative, what they are calling G double dashed of 3 is the same thing as f dashed at 3. And f dashed of 3 is the slope of that curve, that red line at that point, and that slope is -2. When they call it G dashed of 3, isn't that the same thing as the value of the function at 3, which is 3, right? And when they say G of 3, aren't they looking from the area from 0 to 3 of this shape? And that's where the 9's coming from. So that guy there is really the same thing as the value of the function at 3. And this one here is really the same thing as the derivative at 3. And those two you can get from here. The value of the function at 3 is 3. The slope, because that's what f dashed is -2.
Okay.
So that's what was going on there.
Okay, thank you. That one really threw me for a loop because I thought, well, I don't know how to do this since I don't know the function, but I was able to do the first the area and the value.
Right. So you were still thinking in the terms of what you were thinking of it in terms of what the G was doing instead of converting it into what the F was doing, because everything just like shifts one to the right. So a G double dashed is the same as an F dashed.
Okay.
That was the trick. And you said there's another one?
No, I haven't gotten to the other problem set yet.
Okay. And the rest of the questions aren't even like that, so it's not a thing you're going to see much of.
Right. Yeah, that one. I finished, well, besides that question, I finished that problem set last night and I thought, well, maybe it's just that it's getting late and my brain is not working at this time, so but then I still couldn't figure out this morning, so that's why I thought I should ask.
Okay, are you happy with the answer I gave you now?
Yes,
So
thank you.
is that you stick a fork in it, that one's done?
Yep.
Good. You like Calc 2?
I do. I mean, so far it's a lot easier than Calc 1.
Oh, interesting. What's the difference, do you think? Why?
Because I'm using everything I learned in Calc 1, and in Calc
Okay.
1 I was learning it all.
Well, that's okay, that makes sense. I mean, you're building on your knowledge, so it must mean that you're pretty comfortable with your Calc 1 knowledge. And that's why your Calc 2 because it's kind of reversing stuff you already know. Antiderivatives are essentially going backwards. That it's easier. Well, today we're going to be doing substitution rule. So when you do the substitution rule, you're going to have your differentiation cap and your integration cap and your style point cap on. So that's
I'll be back.
You're going to have it, right? Hi, Coachy. How's things? Harrison, Christopher?
Good morning, Professor.
Good morning. Harrison, it looks like you found the same spot that you had last time. Do you have a nice little quiet place you go to do these things?
Yeah.
Don't tell anybody about it or else you'll never get to use it again. Right? Just keep that one a secret.
Sounds good.
From what I'm looking, I'm just trying to orientate myself. Are you in the mesh building?
I'm in the number 4 building.
God, I don't know what the number 4 building is. What's normally taught in the number 4 building? I never keep track of numbers.
I'm not sure specifically which subjects, but I do political science here.
Oh, okay. Is downstairs got the cashier and stuff like that?
I'm right next to it.
I know where you are now.
Yeah.
So am I your only online class?
Oh, I have another online class other than this.
Okay. So the only reason you're in college must be for your on-ground class? Okay. I'm guessing it's a science that needs a lab.
Yeah.
How you doing, John?
I'm doing pretty good.
Good. How's homework going and stuff like that?
It's going well. Understanding it.
It's a good feeling, isn't it?
Yeah.
Yeah. Hi, James. Can't see you. Amber. Come on, let's see your ugly mushies. Am I allowed to insult students that way? I don't know. Amber, am I allowed to insult my students? I just want to check that.
Just not me, so.
Oh, so I've got your permission to insult everyone else, but not you.
Yeah.
I wonder what kind of politician you would make. Probably quite a good one. Amber, how do you tell if a politician is lying to you?
I don't know.
Their mouth is moving.
Oh, that's a good one.
Okay. What's the difference between a politician and a snake?
Snakes don't have legs.
No. Some people like snakes. Okay, I've picked in poor Amber enough. Ismail, Amber has given me permission to insult you. So I'm going to have to figure out how I'm going to do that because I can't think of anything right now. So if you want to chuck in a couple of ideas, I'll go for it. You're not a politician by any chance. That would be a good start. Yep. Well, just to, I don't know why it came to me, but there's a famous quote. I don't remember the exact details because that's my brain, but it shows you how long politicians have been the way they have been. There was a famous Roman statement that went something like, Acronius went to Persia, and when he arrived, Acronius was poor and Persia was rich. But when he left, Acronius was rich and Persia was poor. So even back then, politicians had a bad reputation. Did you hear about the politician who was walking in the streets one night in Washington, and this mugger jumps out with a gun and says, "Give me all your money." And the politician looks at him and says, "Do you not know who I am? I'm a senator." And the mugger looks at him and says, "Okay, give me all my money." You're getting a theme I don't like. I don't like politicians much. Just a little hint.
How about this one?
Oh, you got one. Go, James.
I wrote a letter, but it didn't go anywhere. It just stood still. Any idea why?
No.
It was written on stationery.
James, I can still ban you from this class. I'm sure I could go somewhere in CTC Link and put you in an English class just for badness. So you're gonna have to improve your jokes, so you'll end up having 2 English classes. And
For
trust
real,
me,
one time I got put on joke restriction.
well, today we are, oh, good morning, the last person just came in. Good morning, everyone. Today we are going to start, and tomorrow we shall finish, hopefully, our last section for this week, which is the substitution rule. Sometime last night, I finally got the reports finished, so you should have got an email saying something pretty boring like report 1, and you'll either have it in your OC account email or whatever email you used to do WebAssign. Has anybody seen that thing? Okay, now some of you won't have got it, and it's not that I didn't send it out, it's it didn't arrive. So if you haven't got it in your own email, like whether your private one, the one you used in WebAssign, or in the college one, you will shoot me an email, and on that email you will put the email you want me to use, because evidently the one I've got ain't working, and I will send you back your report. It's not very interesting because what can you do in 1 week? But at least it'll tell you your attendance, your homework grade, and your 0.5% extra credit for not asking for an extension. So let's get stuck right in here. We are going to do a very algebraic lot of work, I guess. Here's my friend over here, the standard integrals. Unfortunately, he's probably going to disappear for a little while because I need him. Because we are going to do a thing called the substitution rule. Substitution rule is very big. In other words, it's very useful. Right now, I would say the power rule is probably the most useful rule you know right now. Right? You can use it to integrate lots and lots of things, right? The power rule. The substitution rule is like a whole division above it. It's even more useful, but it's even more difficult to use. And it has a formula, which I'm going to give you, but that formula is never used. So I'm just giving you it for completeness sake. That's the only reason. And the substitution rule says that if you want to do an indefinite integral like that, then it can be converted into that guy, where, well, that's enough. So I wouldn't even bother writing it down because you're not going to use it. Because the substitution rule is really a process rather than a formula. And so trying to apply that formula would probably not really be feasible. So just said it because I want to get it out of the way in case you ever see it written down somewhere. So let's show you what the problem is. We're going to start with the first ones which are the linear shortcut rule. This is actually, and can be done using the substitution rule, but we can kind of shorten that. Suppose I wanted to do the antiderivative of that guy. Now, right now, the only method that you've got would be to FOIL that darn thing out. Can you see that that ain't going to happen? Nobody in the right mind is ever going to want to do that. If I tried to do that, wouldn't it probably be a couple of pages of paper? And then after that, wouldn't I have to do the power rule about 101 different times? And then if that wasn't bad enough, I should try and factor it all back together again, because style points try and make it look pretty. I have no idea what that do, so I'll make up a number. It'd take you a day, right? So there must be a shortcut. And this is going to be called the linear shortcut rule. What I want you to do is to imagine that this isn't 2x plus 1. I'm going to cover it up so it doesn't look like 2x plus 1. I want you to think of that as something to the power of 100. Right? Some other letter, v to the power of 100, u to the power of 100. So can you imagine that that guy was actually that integral, right? We know how you integrate this. Isn't this the power rule? Great. So you add 1 to the power and you divide by the new power. That looks good, right? Now, how am I going to apply that? Well, you treat 2x plus 1 as a complete object. And so you add 1 to the power and then you divide by the new power. Are you happy with what I just did there? It's a bit of a magic, right? You just do it because I tell you it works. Now, one extra thing has to be done to finish this question off. You don't just say, okay, well, I'll pretend that's x and just do what I would have done if it was x, right? Because that's essentially what I'm saying. Pretend that's just x and do the power rule. But it's not x, it is 2x plus 1. That's the linear part, right? They're always going to be linear. So what you finish with is times a half. Or if you like, divide by 2. So the final answer is 1 over 202, 2x plus 1 to the 101, add c. So this guy here is the integral of that. Does it kind of make sense that it's, although I'm just telling you it works, does it kind of make sense that there are kind of logic to it? It's not just random. Let's try this out. It has to be a linear term. Right, it has to be 2x plus 1, 3x plus 1, 7x plus 9, that kind of thing, for this trick to work. Now, in this case, add 1 to the power, divide by the new power. What do I multiply with to finish? What goes here?
Okay.
Well, it was 1/2 up here because that was 2, but what's it going to be this time?
Third.
Yeah. So you get 1/24, 3x minus 1 to the 8th plus 6 plus c. Would you agree that this shortcut, this linear shortcut method, is very fast? The only other alternate would be to FOIL that out and do a power rule on it. And no, That I wouldn't even want to try that. Now, I guess you could try that one if you really want to prove that this works. So let's try somebody else. We know how to integrate sine x. Let's find out how you integrate sine of a linear combination of x, right? The linear shortcut method. Right. The antiderivative of sine is a negative cosine. So you get that fella times something. When it was 2x plus 1, you times it by half. When it was 3x minus 1, you times it by a third. Oops. What will we multiply this guy by? There's a pattern here.
Is
What
it
do
a
we-
quarter?
And you're all right. Just to make it look slightly pretty. That is the answer to the antiderivative of that fellow. 4 cosine of 5x plus 3. Okay, linear shortcut method. Think of it as 4 cosines of something. Well, when you find the antiderivative of a cosine, you'll get 4 sines of something. Times what fraction? What fraction do I multiply this by?
Is it a fifth?
Yes. Where are all these numbers coming from? Well, 5x gets you a fifth, 4x gets you a quarter, 3x gets you a third, 2x gets you a half. Can you see where that fraction's coming from? Isn't it coming from the coefficient of x? Okay, then let's see if I can make your life even more general. I would like to know the integral of e to the ax. Now we know how to get e to the x, my favorite guy. Let's do e to the ax. That would be like a to the 5x, a to the 2x, you know, things that look like that. E to the something, right, gets you e to the ax. What fraction do you multiply this time?
One.
1? Something else? What fraction do you multiply this answer by? Last chance?
A.
Yeah, 1 over a. Okay, let's prove it the other way. Suppose I had a function and it was 1/4 e to the 4x. Now, if I differentiate 1/4 e to the 4x, isn't the answer 1/4 e to the 4x times 4? Do you see these two guys kill each other off and you end up with e to the 4x? Right, that's me doing differentiation. So if I integrate e to the 4x, the opposite of differentiation, shouldn't I get e to the 4x times a quarter? Do you see going that way? Going that way. I mean, it does work. So the linear shortcut method allows us now to integrate any of these functions here when the x is replaced by some linear version of it. So instead of having an x, 2x plus 1, 5x minus 7, right? You can do any one of these functions and just replace the x by a linear combination, right? A 3x plus 1, for instance. Right. This one seems to be causing more trouble than I thought, but that's fine. the more we do, hopefully we'll get it. Suppose I do this fella. Okay. This guy is a version of this one. Would you agree it's a linear combination of 1 over x? Now, you integrate 1 over x, you should get the natural log of that guy. What else do you do to finish it off with? For the linear shortcut rule to work, there's a last little bit. Yeah, you get that answer, but you also get that answer and you times it by something. What do I times this guy by? What fraction do I multiply him by?
1/4.
1/4. Where did you get the 4 from?
Inside the natural log. It's what?
Yeah, it's that guy there is the coefficient of x. Yeah, James, go the number next to the x. What about the +2? Why doesn't that come here? +2 doesn't matter. That's the only place +2 needs to live, right? It's only the number next to x that's important. That could be +20 or -1,000,000, and that would still just be +20 or -1,000,000. This would not be affected by that second term. Only the coefficient of x's. So you've got to be able to look at these as not carved in stone and you can only have x's. It's much better to think of these things more in a flexible way. So I think of this as 1 over something, and that makes me look at this. Try this for life. Just picking deliberately ugly numbers. When I look at this, I don't necessarily think of it as a 5x plus 2 to the power of 103. I just think of that as a power rule, right? As something to the power of 103. And according to the power rule, the something gets 1 added to its power, right? And then you divide by the new power. And then you go and you focus on what's inside the brackets. In this case, 5x. And 5x gives you a 5th. So what you're going to be left with is 1/520th 5x plus 2 to the 104th power plus c. And if you really wanted to be convinced that this works, take this guy and differentiate him, and I bet you get that guy. Are we slowly getting comfortable with the linear shortcut method as a technique for finding more integrals, right? Now I don't need to worry about only being able to do this guy or 10 over this guy. Can't I do 1 over any linear combination, right? 3x minus 2, whatever. I can now do those guys. And I can do any trick. I think I should do a trick. How about this fella? Secant squared 5x plus 1, and let's stick a 10 at the front. Right. Now I'm looking at that guy, and what I'm seeing is 10 secant squareds. And I know the antiderivative of secant squared is a tan. So it's going to be 10 tans. And then I always remember that when you've got a linear combination, you have to finish with a kind of correction factor, right? A little bit extra to make it all work. And it's always a fraction, isn't it? In this case, what fraction will I use to complete the question?
One-fifth.
1/5. And in this case, I can tidy it up a little bit. This is only one piece of the technique that is called the substitution rule. But hasn't it already took every single one of these integrals and expanded how you can use them? I can now use it for the sine of 7x plus 1, e to the 2x minus 1, secant squared of 5x plus 1, right? I can do it now for any combination. That doesn't need to be x anymore. This can be any linear function, right? Remember, linear, so many x's plus or minus a number. And it doesn't require that much extra, doesn't it? It just maybe an extra line. Okay, I'm not 100% happy with the faces. I'm not insulting your looks. I'm just insulting the fact that you look a little puzzled. So I'm going to give you 3 questions to try out. And if we get these guys, then I'm comfortable and I'll move on. So try and do as many of these 3 guys as you can. I'll be the first one. It's going to be the second one. And that's the last one. Right, if you know what you're doing, you can do those 3 guys in 1 minute, 20 seconds each. So no pressure, go for it. Okay, hopefully you got all 3, but we'll see. I'm going to do a different volunteer for each one, so you can volunteer for every one you want, but we'll start with a volunteer for the first one. Anybody want to go for it?
Yeah, I got 1/27 times 3x plus 2 to the 9th power plus c.
Okay, so you added 1 to the power, and I got you 9th, right?
Mhm.
You did the divide by the new power, and
Yep.
then you factored in an extra times a third,
Uh-huh.
and I agree with your answer. Now as I don't know, as artificial as that looks, there is a theme to it, isn't it? It's not just random all over the place. They're all pretty much the same question, right? The process is the same. So think of this as a process rather than a formula, because there's not one formula that could cover every permutation, right? It's a process that gets you there. Right, somebody else have a shot at that one then.
So 4 secant squared times 5x minus 1. To get our fraction, we take the 4 in front of the secant and the 5 in front of the x to get 5 over x times tangent, because that's the integral of secant squared time tangent 5x minus 1 plus c.
Nailed it. Okay. Now, I definitely made this one a little bit tricky because I stuck a half x instead of the usual 3x and 2x. But isn't a half x plus 3 also linear? Right. Okay, anybody, somebody different again for the last one?
Would it be 2e to the 1/2 x plus 3?
It would. Now, for those who are thinking, what on earth happened to you? Why is there a 2 there? Aren't you essentially dividing by a half? No. You're dividing by 3. That's where that guy turned into 27th, right? You're dividing by 5. That's why that became 4/5. You're dividing, well, nothing there, so I guess it's 1. You're dividing by a half. Right? So that's what that would be like. Okay, I feel better. So now we are going to look at the bigger version of this. We're going to look at the general substitution rule. This guy is going to allow us to integrate virtually like a whole, as I said before, a whole division, a whole like million more things can now be integrated because of this rule. And what we're going to do is show you it by process, by showing you some examples, and then we'll work from that. So here is my first example. And I'm going to rewrite it again over here because I know I need more room. Over here is going to be my working. So step 1, choose the appropriate substitution. Now, in an expression like this, have you noticed that there's a 4x here? There's a big ugly guy to the power of 10, right? When you do the substitution rule, the first step is to pick what's typically called the U sum. We are going to rewrite this integral, which is pretty much impossible to do practically. And we're going to turn it into a much easier integral by a technique called substitution. Substitution just means you replace one thing by another, right? You substitute one thing for another. And we need to choose the appropriate substitution. And typically we will call that substitution U. And in this case, the substitution is going to be that guy. Now, in this question, there's probably only 2 possible candidates for the substitution. The guy inside the brackets or the 4x. That's the only 2 guys in town. Substitutions are never going to be that entire package. Don't even think of that as a substitution choice. Think of the typically one way I look at it is if something's in a bracket, that's probably going to be the guy that's my substitution. So that's step 1. Choose the appropriate substitution. Step 2 is the can't even spell to differentiate. That's a hard word to spell. Differentiate. Show you what that looks like. U equals 2x squared minus 1. So you are going to have 3 caps on. Maggie's got her cap. Maggie, where are you? Maggie, I cannot see you. Where are you?
I'm right here.
Okay, we are going to put Maggie on the spot. Right, Maggie, can you see it? I'm going to change view here. Right. Maggie has got her calculus hat on. When it's in that position, what are you going to be doing?
Differentiating.
Right. Now, where's it going to be when you integrate? Okay. And where do you put it when you do style points? Right. Now, Maggie is wearing a cap.
I think I got those two mixed up.
Well, Maggie is wearing a cap for what you will see me doing, because she knows what I'm like. You'll see me going like this to a fictitious hat sometimes. And what I'm saying is, in this process, you are not just going to be integrating, you're going to be differentiating, and you will be doing style points. So all three things are going to happen inside the same question. And you have to make sure that you've got the right cap on. Oh, I'm in the differentiation mode here, to make sure that you differentiate things. Because if you don't, couldn't you get back to front and integrate when you should be differentiating, and so on and so forth. So that was what Maggie said was about there. And my dog is trying to tell me that there's a leaf falling somewhere. So back to this guy. What does differentiation look like? Well, we are going to use the du by dx notation. Remember, there was f dash notation. This is the differential notation we're going to use. Now, if I differentiate that guy, would you agree you get 4x? Now, you might wonder why we even bother with this notation, because it's kind of clunky. It's very useful for what we're about to do. These things are called differentials, which means that you can actually treat them just like variables. Do you see what I did there? I know I haven't, but it's a bit like multiplying both sides by dx, isn't it, in one sense? Then, so what I do is I call this the crossover, and then you divide both sides to isolate the dx. So step one, pick your u sub. Step two, differentiate. And when you're finished, you will have dx equal to whatever it is. Now, of course, I wrote so big I don't have room for it, so I'm going to put it in here. Step three, substitute. Well, let's see what this thing looks like. I'm going to leave that as 4x. Won't this guy now be called u to the power of 10? Won't dx be substituted with a 1 over 4x du? Style points, I guess, cancel. Do you see that the original integral, the one we're trying to get the answer to, hasn't it been changed into a much simpler, easier integral by this substitution process? Mathematically, this integral is equivalent to that one. But I know how to integrate those guys. So I've got my integration hat on now. My integration hat is add 1 to the power, divide by the new power, stick a plus c. And then step 4, return to the x's. I don't know, I don't want to know that the answer in terms of u is this. Don't I want to know what the answer is in terms of the original variable? I want to know what the answer is with x's. This is what I've got. How do I get to return? I just substitute some more. I replace my u with that guy. So this fella becomes 1/11th. Instead of u, 2x squared minus 1 to the power 11, add c. So what we did is we took an integral that we didn't know how to do it. We used this substitution process to turn it into an integral that was the same equivalent to it, but I know how to integrate. I integrated it, and then I figured out how to turn that answer back into the solution that I was after in the first place, the answer with x's. Isn't that a kind of sneaky technique? You don't know how to do the guy. You turn them into something you do know how to do. You do it, and then you use that answer to get the answer to the thing that you really want. That is a very powerful technique that's used a lot in math. Whenever we get a puzzle that we don't know how to do, one of the strategies is, can we change it into a puzzle that I do know how to do, solve that puzzle instead, and then use the answer to the puzzle we've just solved to figure out what the answer to the original problem was. Sneaky. That's called the substitution rule. Show you another one. Right. Would you agree we do not know how to integrate x e to the x squared? You will not find an x squared in here, right? You won't find an e to the x squared. And you definitely won't find an x times an e to the x squared, right? So right now, we do not know how to do that. What would be the u sub you think I should use here to get this show on the road? You've only got two candidates.
Would it be x squared?
I would.
Yeah.
Why wouldn't I pick x? Just for the argument's sake. Why is x a pretty useless substitution?
Because you're just like swapping the name of x itself. You're not changing anything about the formula.
Yeah, doesn't help, right? You end up with the same guy you started. Now this guy, now you differentiate with respect to x. So you've got your differentiation Heartland. You then do the crossover. Right? And then you divide both sides by 2x to isolate the x. So you think about isolating the x. That's the whole trick. So I've got a u sub, and that u sub is now going to allow me to replace the dx by something else. Now you go over here. Leave the x alone for a moment. E to the x squared now becomes e to the u. The dx becomes 1 over 2x du. Do a little cancel. And now, almost like magic, hasn't our question now turned into an integral that we do know how to do? I know how to integrate that. In fact, it's pretty easy to do that one, isn't it? And to finish with, now that I've got the answer, shouldn't I turn the answer into things that has x's? Because that's the answer I was wanting, right? The answer that used x's. Well, I've got a half e to the u plus c. Isn't u x squared? Have you noticed that it's basically just substitution? Sneaky. Any questions about that? You know, you've only seen a couple of them, right? So it does take a little while for your brain to become used to the process because it's a process. Let's try another. How about would you agree that there's no way in the world I could integrate that using standard integrals, right? Ain't happening. Right? There's no algebra that will fix that, right? I can't FOIL things out and make it nicer. I have to use the substitution method. Who will the u sub be?
X cubed minus 1.
Well, yeah, the plus there, but my grade. That one. That is the right one. Why did you choose that one?
It is the ugliest looking part of the question.
That is a very, very good way of describing it. Look for the ugliest bit of the thing. And it's typically, although it's not got brackets around it, imagine there was brackets around it, it's typically got some brackets around it. And that's 9 times out of 10, that's going to be the best way to choose the U sub. Now, once you've got your U sub, you differentiate with respect to X. You then do the crossover. And then you isolate the dx. Have you noticed that that's pretty standard? Once I pick this guy, doesn't the next few lines just follow as they do? Now you then go over here and you start some substitutions. I typically don't do anything to that guy. I turn him into a square root of u. I replace the dx by that guy. And then I tidy up. And has it my question now turned into an integral that I do know how to do? Okay, maybe I've got a little bit of work on it, but would you agree we all know how to integrate 2 square root of u? So what we do is turn it into a half power. Add 1 to the power. Divide by the new power. Use style points on it. And what do I do to finish this question off? One more step to finish this question off. What do I do next?
Substitute back in the X.
In this case, now come on, that is pretty impressive that we now have a technique for integrating some of the weirdest, strangest looking things in the world. Great. Pretty good technique. Now I'm going to kind of do a side issue here for the next 6 minutes because that's all we've got left. So while I'm getting ready to do the next thing, will you put your name in, last name, space, first name? Right, let's do attendance right now. Last name, space, first name.
I put in a comma. Sorry about that.
I'll figure it out. Or actually, if you do it again with a space, it'll organize it and I can take out the duplicates. Okay. Now, what you should be looking at, everyone, I hope, is section 5.5, substitution. And what we're going to do is just one job. Getting practice at picking who the U sub is. That's the only bit we're going to look at, right? Because if you don't get that right, the rest of the method ain't going to happen, right? So you need to be good at that. And I want to do that so we can get practice. Now, they're quite nice at the beginning. Do you see they're telling you who the U sub is, so you don't need to worry about it? But let's just look at it anyway. Would it be pretty obvious that's the 2x? Can you see this one? They've decided on the negative x squared, right? So I'll try. Can you see why the U sub is x squared plus 5 here? So some basic rules. If it's the sine, cosine, or tangent of something, the something is your U sub. If it's e to the something is your U sub. If it's ugly square root, the thing inside the square root is your U sub. You see the rules I'm putting in English? Okay. If it's a fraction, because we haven't done one yet. right? If it's a something on top over something on the bottom, 90% of the time it's going to be the guy in the bottom is your U sub, right? And the reason I'm saying 90%, unfortunately, there's a little sophistication here. 1 out of 10 times, all bets are off. The U sub that it should be obvious does work 9 times out of 10, but 1 out of the 10 times it won't work. In which case, once you've figured out it doesn't work, you have to figure out some other weird guy instead. Now, I guess that one qualifies under a lot of reasons. Isn't it the ugly guy inside the cosine? So square root of t would have been the U sub there. Inside the square root. Okay, here's the first guy that we actually have to pick a U sub for. What is the U sub in question 8?
Minus x squared.
Agreed. What's the U sub in question 9?
One over negative four.
Oh, that's what you've told me is later on the answer. But what's the? You're correct. That's going to be there, but that's not my question. What is the U sub in question 9?
Oh, the substitution would
Yes.
be, sorry, would be 9 minus 4x.
Right, you're ahead of me. You're doing the bit that comes after that.
I'm sorry.
Nah, you're good. We're talking about the U sub means the substitution, right? That's my shortcut for the substitution. So what was the substitution in question 10? Any volunteers? Substitution in question 10.
Negative 10 to the 9th. Negative t to the 9th.
Yeah. Actually, t to the 9 on its own would also work. So sometimes you know, 2 answers work, and that's okay. Both work. Oh, there's an interesting one. What's the U sub in this question?
1 plus cosine t.
Yep. What about question 12? What's the U sub going to be?
9 theta.
Yep. 13, what's the U sub going to be?
4x plus 9.
Yeah. If it's a fraction, the guy in the bottom's a good candidate, isn't it? 9 times out of 10. Okay, really ugly looking 14. Who's the U sub?
Nine minus y power to 3.
Yeah. I'm skipping by trig because trig has its own rules, as you'd expect. Trig's always awkward, right? So I'm not even going to talk about the trig one. There's a strange looking question. What's the U sub?
Negative 8r or
Okay.
8r.
Yeah, both will work. There's one where you've got a bit of a choice here. It's a fraction, so it should be the guy in the bottom, but it's got an ugly bracket squared, so it should be the guy inside the brackets, right? So only one of those two is the correct U sub. What do you think the correct U sub for question 17 is?
8 minus e to the power of u.
Correct. Can you kind of see why that's probably going to work better than the other choice? I don't think I've done an example of 18, but it's here, so we'll talk about it. Give me a U sub for that ugly guy. And you might be surprised to know what it is. Because it's one of the 1 out of 10, right? 9 times out of 10 this works, but here's one that doesn't work. Because normally you would say, I'll pick the bottom guy, right? X to the 8 doesn't work. So you try it, you play about with it, this is going nowhere. Okay, back to square one. What do I do? What do you think the U sub's going to be then? Because that doesn't work.
1 over x to the 7.
It's actually the one that does work. So you are going to get questions where the basic rules, you know, the ones that work 9 out of 10 times, don't work for you, right? That's going to happen now and again. Not a lot, thank goodness, but occasionally. And when that fails, aren't you just going to go and say, and how will you know it fails? Well, say when you do the working, instead of getting a nice integral with only u's in it, you get an integral with x's and u's, that are, you know, hey, there's bits left over, this isn't working. That's what you'll notice. 19 looks ugly, but actually the answer's dead easy. What's the U sub?
Nine AX plus BX to 9.
Just pick the guy inside the square root. That's a 9 out of 10 one, right? Inside square roots. Takes priority over fractions. In this case, won't it just be the fraction? So the entire bottom. Here is one, this question here, where you have to pick a less obvious U sub. Well, to me, it's not. To me, it is obvious, but maybe it isn't to you. What would the U sub be in 21?
The natural log of x.
Yeah. So that was obvious to you as well then, Ismail. Some people get a little bit confused because it's a fraction. But can you see in a fraction, making the U sub equals x doesn't help, right? I'm skipping the trig ones because they don't work. What would the U sub in 24 be?
X plus 7.
Oh, hate it, hate it, hate it. Ah. Oh, God, you got to stop doing that. Okay, I'd be happy if somebody could tell me the U sub here because it's one of the weird ones. It's not an obvious one.
Or cosine X.
Yes, but you used the wrong word. Inverse sine of it, cosine. No.
Okay, sorry.
Yeah, you should be. That one's a trig one. I skipped them by. This one is inverse tan. What do you think 20 is?
8t.
Yeah. What do you think 29 is? You should get a brownie point if you get this one.
Pi over x to the power of 37.
Yes, it is. That's surprised you got that one so quick. This one's just the bottom. That's a trig, forget it. That's a trig, forget it. This one, let's stop there. The last few are all special cases, right? So I feel a little bit more comfortable than I kind of did at the start. Are we beginning to get the idea of this U sub technique, right? This substitution technique. By tomorrow, we will be really good at it. So bye-bye, everybody. I'll see you tomorrow.
I have a question real quick.
Yes.
I missed class yesterday and the day before yesterday
Yes.
because I had no Wi-Fi.
Uh-huh.
And then tomorrow I won't be here because I have the SAT. So
Your
wait.
life is busy.
actually,
Okay,
I have
yes.
I have a dentist appointment tomorrow. It's not correct. Not good.
Okay. You're not going to be here tomorrow for a reason, a good reason.
Yes.
So there's a question at the end of this because that's information.
Yeah. Would it be all right if I could get those made up for the grade? Because I have no way of being here.
It's difficult for me to do that. So let me tell you the workaround for that. You're expected to watch the videos of any days that you miss. That's sure.
Yes, and I have.
That's sure. Right. So what you're going to just, it won't directly affect your grade because as long as you do your homework on time, you'll get the extra 0.5% extra credit. And that
Okay.
will more than compensate any days that you've missed. So
Okay.
theoretically, your grade won't change as long as you know, if you don't turn up at all, you'll fail. But I mean,
Right.
as long as it's a few days, it won't really affect your grade to any great extent.
Awesome. Thank you very much. You have a good day.
You do. Any other questions? Because I'm off to my next class.
I do have a really quick question.
Go for it.
So on one of the problems in the WebAssign that you just showed us,
Uh-huh.
it was, I think it was sine pi divided by x to the 30 something or other.
I'm looking for
Would
something that looks like that. Do you have a number on it?
It was sine of pi over x to the 37.
Okay, yeah. Do you have a number on that? I'm still trying to find it. I'm scanning back. Probably I went by too quick. Let me slow down. There it is. I found it. Okay, so it's probably a version of this. If it's not that one, it's the one I think it is. Is it this one here, number 18? Oops. Share the screen properly. Right, is it that one?
No.
No, okay, keep going. That one?
Yes.
Okay.
Okay, so this is probably a really stupid question, but does
Mhm.
the 37, since there's no brackets around the pi divided by x, does it apply to the whole quantity pi over x or to the x?
Only to the x.